what's the product? So you want to look at the slides and see all the abbreviations for these different acids. Pretty much yesterday's discussion was all on this para-sulfonic toluene. And this thing here is the, let me fix that up. This thing here is the chloride version. And both these work very similar in that we form this thing called the tosylate. And it might be called a tosylate ester versus like an ether. But instead of carbonyl carbon, we got a sulfur. So what's the beauty of this thing? Good leaving group. So SN2 reactions, elimination reactions, and so this is a big curveball. None of those occur. What do you know about lithium aluminum hydride? Is it an oxidizing agent? True or false? What? False, right. What kind of reagent is it? Yeah, reducing. So if I reduce an alcohol, what do I get? Right, so this is kind of, here's what you get. We remove the OH group. So this might be abbreviated a couple different ways. It might be the acid or the acid chloride. The point is they all work the same. They react with an alcohol, and then you can do elimination, substitution, or if you hit it with lithium aluminum hydride, you can reduce it. So reaction with alcohols with acid, you've seen some of this already. You protonate a hydroxy group, it starts looking kind of like hydronium, and that means it's a good leaving group because water can leave. So if I imagine something like hydrogen bromide, strong acid completely disassociates, protonates that, and then the halide can, boy, don't follow my fingers on that one. Let's just imagine we have HBr. It could be aqueous or it could be in the solution of the alcohol, probably more likely. So this would be a mechanism, grabs that, gets protonated, and then my favorite B movie, Attack of the Halide. So alcohols, we can make a good leaving group by protonating the OH or forming the tosylate ester. Once the alcohol is protonated, substitution or elimination can take place. And here we see if we use an acid like this, we pretty much get that alky halide. So here's a typical alcohol, cyclohexanol, bromocyclohexene. Tertiary and secondary alcohols react with Br via SN1. And that's always true with the tertiary. That's something you want to remember from last year. That's an absolute. Tertiaries don't like to undergo bimolecular substitution, but the OH can get protonated and then leave and forming a tertiary carbocation. Remember, carbocations are a species in the unimolecular reactions. And then of course a primary, we'd have to predict bimolecular. So here's a tertiary alcohol, protonate the OH, becomes a good leaving group, it leaves, form a tertiary carbocation, and then attack of the halide. Bromide attacks the carbocation. And here's our tert-butyl bromide. So here is a, look at that, primary alcohol. OH is on a carbon that's only connected to one carbon, that makes it primary. Protonate it, and then the halide attacks. And they're showing inversion even though we got two groups that are the same, meaning we don't have our four groups to make this an asymmetric carbon. But that Walden inversion is a hallmark of SN2. HCl, very similar. Chloride is a weaker nucleophile than bromide because it's small and less polarizable. So if we add some zinc chloride, it's going to bond strongly with the oxygen on the OH, and it promotes the reaction. We might call it a catalyst. guy who figured this out must have been named Lucas. And so there's this thing called a Lucas test, where you make up some zinc chloride and concentrated HCl. Then if you have an unknown alcohol, you put it in a test tube, add some of this reagent, and the alkyl halide, you should realize, is not soluble in alcohol, well, smaller alcohol anyway. Well, let me just back up. This is a very aqueous type solution here. So the alcohol, so the smaller alcohol can be soluble in this, but when it forms the halide, you get 2 layers. So you watch your test tube and see how quickly the 2 layers form. If you add it, shake it up, within 60 seconds, you get 2 layers, you got a tertiary alcohol. If it takes 5 minutes, probably a secondary. If you have to wait a day or you don't notice anything, most likely a primary alcohol. So here the zinc chloride bonds with that. It's kind of like being protonated. Lowers the transition state energy. The halide comes on there. This thing leaves. So the reaction is very slow for the SN2 mechanism. The reaction can take from several minutes to several days. So here's a secondary alcohol. The zinc chloride makes this a good leaving group, catalyzes the reaction, or the leaving group leaves. Halide attacks the carbocation. So secondary alcohols react a lot quicker and by an SN1 reaction. So alkyl halides are very versatile, as you know from the fall semester. There might be some limitations with making alkyl halides from alcohols with hydrogen halide acids. We get poor yields of alkyl chlorides from primary and secondary alcohols. We have elimination can compete with substitution. And then, of course, carbocation intermediates can cause rearrangements. And so if we're after ways and means to make alkyl halides, this is good for theory of organic reactions. In early days, a lot was made that way. But there's a superior reagent with phosphorus halides. And we get good yields with primary and secondary alcohols. And so here's phosphorus trichloride. And here is a reagent called thione chloride. Works better than phosphorus trichloride. But this phosphorus tribromide is great. We can use that to make alkyl bromides from alcohols. Phosphorus and iodide to form alkyl iodides. They're not stable. Reduction products can be formed. So here's a primary alcohol. It's kind of sterically hindered. And we get the halide, 60% yield. Here's an alcohol, pretty good yield of the alkyl iodide. Secondary alcohol, good yield of the alkyl halide. So what is the mechanism? So this is analogous to protonating the OH in that we make an excellent leaving group. And then the key point here is the halide attacks the carbon. And this looks like SN2 because there's no carbocation. Oxygen attacks the phosphorus, displacing one of the halides. Presumably that halide attacks by the backside SN2 reaction. So we're going to back up for just a second. We want to compare and contrast doing a SN2 reaction with a tosylate ester and versus using the phosphorus bromide. And the point being here is when we form the ester, it doesn't affect the stereochemistry of this carbon. Because when you form the tosylate ester, it's a condensation reaction. I tried to call it hydrolysis, that's the opposite. Looks like if we added a bunch of water, we could go that way and call it hydrolysis. cleaving this bond with water. Going the other way, we call it condensation. Get some water out of it. Now I'm drawing models like a student. Now I want to draw the same enantiomer here. And here I want to do one of those tosylate esters. TSOH. Or I could use TSCl. And let's make this interesting. Sodium azide. So that's that thing there. Only it doesn't look right. That doesn't look any better. Let me just go back to basic chemistry here. Roman numeral 5 should have 10 electrons. 2, 4, 6, 8, 10. I'm gonna stick with that. So, instead of just telling you the outcome and saying that's the way nature works, so we saw that this phosphorus thing protonates the alcohol or kicks out a halide, then the halide hits this thing. So I'm going to draw my wedged and dashed wedged in here. And so this hydrogen that was there, I'm gonna put here like that. All right, now this, all the chemistry occurs right there on the oxygen. Oh, don't ask me about that. I just lost all my points. You don't put 5 bonds on a carbon. Top one? Thank you. All right. So the point here, this hydrogen's gonna still be there. And here I'm gonna have this tosylate. So here's one inversion of the stereo center. And then when the nucleophile comes and hits, and so this is really like 2 SN2 reactions occurring twice on this carbon. First one when the bromine hit, and then the second one when the azide ion hits. All right, hang on. So today's take-home message is we can have control. If we have an alcohol, and just for review here, let's figure out the configuration. So something that's new is the left hand and right hand rule. I think it's genius. How did it work? You put your thumb in the direction of the low priority, the hydrogens. So this one's relatively straightforward. I'm gonna give this oxygen highest priority. That one's second, that one third, that one fourth. So this looks R, right? That means it should follow this right-hand rule that says put your thumb pointing in the direction of the lowest priority group. And then my fingers will curl from OH to that one around. And it works really good when you have a hydrogen sticking out at you. It's the whole reason why you do this. And so if I stick my thumb going back because the hydrogen's going back, my hand doesn't circle around. This thing's got to be R as well. Oh, looky here, we get to use this. So I'm going to cheat. I know it got inverted. It should be S. Here's my left hand for S. And I put my thumb coming out. And look, I'm going to go bromine to that CH2 to that CH3. Bromine, CH2, CH3. Thumb's pointing out because hydrogens. So this is S. Now I'm going to come over here, and luckily nitrogen's to the right of carbon on the thing, and this is double bonded. This is going to be my highest priority group. Hydrogen's in the back. N2, the CH2 there, clearly R. Now, with the tosylate, all the chemistry is cleaving this oxygen-hydrogen bond when we form the tosylate ester. Sorry I didn't draw it all out. And so notice, this is an oxygen bonded to that sulfur, double bonded to the other oxygens. This is still clearly the highest priority group. Tosylate, CH2, methyl, thumbs pointing back because of the hydrogen. So this is R. then it gets inverted. Got my thumb pointing out. Look, I got the wrong hand. I can't go methyl CH, or actually I'd be starting with the azide group. Got to get this hand, and I can go azide, CH2, methyl, thumbs pointing out, and so this is clearly S. So if we have R, an alcohol of R, and we want to put another group on it, and we want our product to be R, we could probably use the phosphorus bromide, and that affects 2 Walden inversions, gets us back to an R stereoisomer. If we want the S and our alcohol is R, we would go the tosylate ester route, and then we get 1 Waldo inversion. That is the highlight of today's lecture, and you notice I burned up my last PowerPoint slide, so we will adjourn for today.